really broad sweeping generalisation to start with, which is the universe is made up of stuff.
Whoa.
The stuff that we're interested in, though, is the charged particles of protons and electrons. And this gives rise to electricity as we know it, and the ability to apply that to things like electronics and radios, which are what we're interested in. Those charged particles can flow. Static electricity is a good example. Lightning is a pretty scary example, etc. So given they've got charges, there is electrical potential involved. If they have like charges, then they tend to repel. If they've got unlike charges, they tend to attract. That says that there's a force involved. And that force, and if you apply that force along a conductor, and we'll go into what a conductor is, as an ordered movement of these charged particles, then we call it current. So a current flows in that conductor. And we can measure that. We measure it with a thing called amperes, amps, and we represent it with the letter I. So you just need to know the concept of current. It's the flow of electrons. In conventional electrical terms, it's the flow of electrons from a negative terminal of a battery to a positive terminal of a battery through your circuit. Now that's the conventional wisdom. So if you go onto YouTube, you'll get 15,000 other ideas about that, but that's the conventional wisdom that we use in this training. A battery is a chemical reaction, has a chemical reaction that supplies those electrons to push that current around the circuit. We call it electromotive force. So it is actually a force along that conductor. That electromotive force we actually call voltage. So it is a flow of electrons from positive to the negative. Voltage, we call that voltage. It's the force of those electrons along that conductor. Now, the confusing thing is some training represents it as V or E. We're representing it as E. That's that through the literature and the foundation manual. It's E. So that's voltage. So if you see E, you know it's voltage. If it's I, it's current. A higher voltage equals a higher pressure. So you're able to push those electrons along that conductor even faster. And there's this concept of there being, you can raise the voltage to a point where circuits fail, so excessive voltage, or if you have the positive and negative around the wrong way on a battery, if you've ever done that and you've let the smoke out of the device, the magic smoke out of the device, there is this concept of polarity and getting the right polarity in electronic circuits. Now I talked about conductors. Conductors allow those electrons to move through it really easily. Most metals are good conductors, and a good example is all our wiring in houses are usually copper, because they're good conductors, allow the current to flow. The opposite to that are good insulators, and I'm glad there are good insulators, because if there wasn't, then I'd be able to touch the conductor, which is a safety issue. So an example of insulators: plastic, dry wood, ceramics, porcelain, glass, etc., etc. Plastics extensively used. So, and insulators, you have to apply a much, much higher pressure to get insulators to conduct, and it usually means the insulators fail because you tried to push so much through it. So yeah. There's this concept of this flow of electrons, a constant flow of electrons, or direct current. So it flows in one direction from one side of the battery to the other, or one side of the power supply to the other. If we represent that on a chart where we've got, it's either positive or negative, and this is time, it's just a straight line. doesn't change, same voltage for forever unless the battery goes flat. Then there is alternating current. Now, alternating current is what comes out of your main socket, and what it means is it alternates. It goes positive for a certain period of time, then it goes negative, and it cycles through that. A good example is what comes out of your main socket, and it's doing this 50 times a second, or 50 hertz. We'll go into that in a sec too. So if you increase the size or the length of the wire, you actually increase the resistance of flow of electrons. So if you make the wire longer, there is greater resistance in that flow. Or if you make it thicker, there is less resistance because you've got greater surface area for that current to flow through, those electrons to flow through. What you can do though is crank up the voltage or the pressure, the electromotive force, and push those electrons down that wire. Now what usually happens is that wire then starts to get warm, because if it's not big enough to carry that amount of electrons, and the friction or the resistance of flow converts into another form of energy, which is normally heat. Now, resistance. So we've measured. This is the resistance to electrical flow. We can measure that. It's represented by R, and we also use a Greek letter omega to represent it as well. So you might see R, or you might see a little squiggly line. It's the opposition to the flow of electrons. Now, in electrical circuits, you don't need to know the actual colour codes, but if you go on to standard and advanced, you need to know the colour codes of resistors. These are really small normally. You need magnifiers to see them, and the way that they put the value on there is via a colour code. You don't need to know the colour code, but most resistors you can see there are bands of colour that specify what the value of that resistor is. And the size relates to how much power you can put through it. And I'll go into power in a sec. Now, this is as hard as the maths gets in foundation. Ohm's law. Ohm's law, and there's a bit of an aid memoir here with the triangle. So the triangle, if you represent E, which is voltage, over I and R, what you're able to do is cover up the value that you don't know, and the triangle tells you the formula to get the value you don't know. So if I'm given a current and I'm given a resistance and I need the voltage, then what it's telling me is it's I multiplied by R to get E. If it's, say, I'm given a voltage and a current and I need to know the resistance, then it's the voltage divided by the current. And that's the formulas over the other side. So one of the things you get as part of your exam is a scribble sheet. If you're having trouble remembering Ohm's law, the first thing I do is scroll the triangle and EIR on the piece of paper, and you can work it out from there. So this is as hard as the maths gets in the foundation. You need to know Ohm's law, voltage, current and resistance. Any questions? And the exam question you'll get is, for a voltage of 2 volts and a resistance of 10 ohms, how much current? And there'll be 4 possible combinations. Now, you also need to know about the concept of power. Now, the definition of power is derived from our voltage and current definitions. So 1 volt applied to a circuit causing 1 amp of current to flow through that circuit will cause 1 watt of power to be dissipated. Now, probably you've been exposed to, or plugged a lot of things into a PowerPoint and the circuit breaker's tripped. So if you added up all of the power ratings of all of those things, the heater and the hairdryer and the iron and the burn and the whatever, and it added up to more than 2,400 watts, so 2,400 watts, then more than likely the circuit breaker on that particular PowerPoint will trip. And so there's this concept of things consume an amount of power based on obviously what they are. So, and a good example that we've actually included here is one of the reasons why you see those very large gantries with heading across the countryside with wires on them. So these huge towers with very high voltages on them is, you think about it, if they generate the power at a power station somewhere up in the Central Highlands of Tasmania, and if they were having to then distribute that power at a low voltage and a high current, which is what they generate at, and they needed to send that a couple of 100 kilometres to Hobart, they would need a very large cable, a very large and very expensive cable for a couple of 100 kilometres, because the losses involved in that cable would be phenomenal. So what they do is they bump up the voltage and lower the current. Now the problem with bumping up the voltage is scary voltages need big insulators because they tend to do damage if they get out of control. So that's why they need big towers, and it's really high voltage but quite low current. When they come into town, they then transform that down so that the voltage goes down but the current comes up. So as they get into suburbia, it gets further and further down to your 240 volts and 10 amps in your outlet in your home. And what that does is cut down a lot of the losses involved in power distribution. So any questions around power? Now, you don't need to know all of these formula. But the one I've highlighted there, which is power is voltage times current, is probably a good one to remember. The other ones are derived, so you can derive if you've got resistance and current. But the easy one is, so if you've got 240 volts comes out of this and it's capable of delivering 10 amps of current, how many watts have we got?
Just earlier,
2,400, well and truly, because it's 240 times 10. So that's how you work out the power rating. And if you look at the back of appliances, it will have a power rating on it. Probably have a voltage rating on it, so you're not going to plug into something that's not the right voltage, but it'll have a power rating on it, like 1,800 watts. So as soon as I plug that in and turn it on, there's 1,800 watts of power being consumed. Any questions? Okay. Now, as we go through, there are some slides which have practical on the top of them. This is something we will get you to do as part of your practical, which is symbol identification. Now, the assessors will show you a sheet which will have those symbols on it, but they won't have the names next to them. So, what we've got is resistance, resistor, a speaker, a switch, a cell, so a battery cell, an antenna, which is the one that points up, versus an earth, which is the one that points down. We've got a battery, which is a whole lot of cells all put together. We've got a fuse, which is the squiggly line, a microphone, and a lamp. So, and we'll just, as an assessor, point at each of those and ask you what the symbol represents. So that's part of it.
Why are there always lamps in radio circuit diagrams? What's the lamp do?
Well, it's a light. So
Going
it can be a power supply. You switch a power supply on, the lamp comes on to tell you that the power supply's on. It can be as simple as that. And can I just say, it probably is not represented as that in the circuit diagram. But anyway, that's the OCMA requirement. So, okay. In electronics and in radio, we deal with things that are really big and things that are really small. If we were having to write all the zeros down relating to things that are really small and things that are really large, it would drive us crazy. So we have prefixes that we assign. The ones that you need to know about in the foundation syllabus are the 4 down the bottom that are highlighted. So mega, which is a million, kilo, which is 1,000, milli, which is 1,000th, and micro, which is 1,000,000th. So mega and kilo are at the big end, and milli and micro at the really small end. You don't need to do conversions between these, but if you go on to standard and advanced, you do, which is really confusing. Can be really confusing. So here's some examples. 22 kV, 22,000 volts. There's 1 meg ohm or 1 million ohms, that's a resistor. 15 milliamps or 15 thousandths of an amp, or 120 microamps or 120 millionths of an amp. So you need to have a bit of an idea about mega, kilo, milli and micro. Now I mentioned that the mains output was at 50 hertz. So we measure frequency in hertz, thank you to Heinrich Hertz, who discovered alternating current. It is the number of cycles per second. So power is usually tens of hertz. When we get up into the radio spectrum, it can be hundreds, thousands, millionths of a million hertz, so million cycles per second. What we can hear is what we call our audible frequency range, which is 20 hertz to 15 kilohertz. Now, you need to probably be pretty young to hear 15 kilohertz. That's your mosquito. And as you get older, that top end comes down. In radio, we talk about a voice frequency range for radio telephony, which is voice, of about 300 hertz to 3 kilohertz. So you might hear that somebody says, my transmitter has a bandwidth of 2.7 kilohertz. Okay? That means that it can transmit a voice in the range of 300 hertz to 3 kilohertz. A bit lower than 3 kilohertz, but it's got an ability to transmit a voice or a frequency range. Alternating current has a frequency, which we talked about, so cycles per second. It has a wavelength. So one wavelength is the time it takes to do one cycle. From goes positive, then it goes negative and back to zero as well. So that's a wavelength. The period of that wavelength, so the amount of time, and it is one cycle that it's going through. Now you don't need to know this particular formula, because we give it to you in a chart that I'll go into in a sec, but because the speed of light is constant, we can then work out wavelength if we've got frequency, and vice versa. If we've got frequency, we can work out what the wavelength is. And amateurs can be really confusing because they'll talk in frequency or wavelength and they just interchange between the two. we'll say that it's the 40 metre band. Well, that's 7 megahertz. Now, how do we work that out? If there is a question in the assessment relating to frequency and wavelength, this chart will be included with the question. The way you use this chart is if you're given frequency and you need to work out wavelength, you find the frequency on this scale and say it's 20 metres. So 20 metres is you're given the frequency of 14 megahertz, so it's around about here. You zoom across here to the red line and then come down, and it's about 20 metres. So if one of the answers is 20 metres, that's the one that it would be. And vice versa, if you're given, I don't know, you're given a wavelength of 40 metres, somewhere in here, up here, across, and it's about 7 megs ish. So you can, either way, if you're given wavelength, you can get frequency. If you're given frequency, you can get wavelength. And you're given this chart. So you don't have to work out the formula. This is the formula in chart form. Any questions? Okay. Now, on the chart up there, we split up these ranges of frequencies. And they're 300 kilohertz to 3 megs, medium, 30 megs to 300 megs, very high, VHF, 300 to 3000, UHF. Now, people talk about UHF-CB. It is in that, it's in the around about 400 megahertz, so that's why it's called UHF, because it's in that band. 27 meg, it's HF, so it's in the HF band. It's that sort of thing. So we split these up for convenience, and that's how the chart represents it. Some of the sort of questions you might get. Electric current is?
C.
Good conductor?
D.
Now they put in A, which is a bit confusing because A is what we call semiconductors. They sort of conduct.
Germanium is what you can make that infrared glass out of.
And transistors and diodes. In fact, there's a germanium diode on this crystal set, which I'll hand around shortly, and you can actually see one up close. Okay, here's your Ohm's law question. 10 volts applied to a circuit consisting of a resistance of 5 ohms. Now, EIR, EIR, voltage over resistance equals current. So it's 10 divided by 5. That's B. That's as easy as it gets. That's, as hard as it gets. Hard as it gets. It's easy. So I hope, please don't worry about it. And the thing about it, scribble down EIR on your scribble sheet as soon as you get it if you're having trouble remembering it, because you can work it out. Okay, 1000 volts is often represented as
1 kV.
1 kV. K is 1000.